I took a look at the Spectral Theorem in multiple linear algebra books, and there's even a cameo by Sheldon Axler's Measure Integration and Real Analysis book for this particular topic, which I found very interesting. I'm going to get started with Anton because Anton actually has a really good start, and since it's an intro book and one that I covered, I just wanted to start with it. And so here it goes. So there we go. Spectral decomposition. So a symmetric matrix that is orthogonally diagonalized by P, all right? And if the eigenvalues of A corresponding to the unit eigenvectors, then we know that a diagonal matrix is equal to P transpose AP. Of course, we know that D is the diagonal matrix of the eigenvalues. And so then you can break out A into a spectral decomposition that is the eigenvalue times these orthogonal projections, all right, multiplied as such. And of course, Anton has a really nice example and even a segue into Schur's theorem and Heisenberg's theorem. So I'll stop there for Anton and then move on to our dear friend FIS. So in the case of FIS, and I'm going to zoom in more because Anton is a bigger book. Let me see if I can line it up correctly here. So in the case of FIS, they take a much more theoretical route, still explaining with vectors what's actually happening in the spectral decomposition. And here's the spectral theorem with a long detailed proof, which Anton does not have, and a corollary for F equals C. In using a polynomial, g of t, where t is the operator. So yeah, so in the case of FIS took a very theoretical route, and as I mentioned in another video where I made an update, I would have liked it if FIS had an example for the spectral theorem. So then now if we switch over to Stang mentions the spectral theorem. I wouldn't call it in passing, but it gives it a brief treat, similar to Anton's. So here we go. Again, your real symmetric matrix, and it's diagonalized. And of course, then you can make a spectrum out of it. So this is exactly the formula that is used in Anton. And there is an example. And that's that. So basically, Stang and Anton give it a very similar treatment. Then if we go over to Huffman and Coons, which I've been reading in my commute. Great book. I really want to do more of it as I finish up my first tour of linear algebra. So in the case of Huffman and Coons, and I always mispronounce the name, I'm just going to acknowledge that I do. They have the spectral theorem, and of course, it's just as I mentioned before, with the operator being broken up by these orthogonal projections. And then, of course, they also have a proof. So the decomposition, of course, that we're talking about is called the spectral resolution of T. This terminology arose in part from physical applications, which cause a spectrum of a linear operator on a finite dimensional vector space to be defined as the set of characteristic values read eigenvalues. That's what Huffman and Coons calls eigenvalues for the operator. It's important to note that the orthogonal projections are canonically associated with T. In fact, there are polynomials in T. So that is where Huffman and Coons leaves it. Then in the case of Axler is very interesting because Axler discusses the spectral theorem, talks about the real case. You see if I line up the book with the camera, sorry about that. And then goes about the minimal polynomial and talks about the real spectrum theorem. It has an example. And then talks about the complex spectral theorem. So he's got a pretty good coverage. But the thing that I also really like about Axler is that he puts in a plug for his Measure Integration and Real Analysis book, section 10D. I found this very interesting because it is one of my very long-term plans to cover this book also by Axler. And so the chapter is called Linear Maps on Hilbert Spaces. And it's got a flavor very similar to all the operator work that is done in chapter 6 of Friedberg-Insel-Spence. That's what I mean by FIS. And then down here towards the end of the chapter, there is a tie-in to what, and this is what Axel was mentioning, section 10D. And section 10D is the spectral theorem for compact operators. So there it goes. It gets its own treatment in this functional analysis book that Axler wrote. And so it's a great tie-in between linear algebra and functional analysis. I'm not going to go through it in detail for this book, but I just wanted to briefly mention the spectral theorem is actually pretty important, and I'm really glad that I've gotten it to cover it in my first linear algebra go.